Okay, in this section we're going to look at the three basic laws of logarithms, and these are going to be true of logs to any base. I should have put a little b down here. Okay, so this is true for base 10 logs. It's also true for logs of any other base. And let's go through and just first of all see what these properties are. So the first one says that you can take the log of the product of two numbers by taking the logs of the individual numbers and adding them. So the log of a times b is the log of a plus the log of b. That's sort of interesting because we can do a multiplication by actually carrying out an addition if we figure out the logarithms first. Okay, look at the second one. The log of a ratio, or the log of a quotient of two numbers, can be found by subtracting the logarithms. So we can basically do a division problem by actually carrying out a subtraction problem instead. All right, and finally you have the log of a power, and this is one we saw in the previous section. The log of a power is the product of the power times the log of the number itself. Okay, so the x could be brought down in front as we've done before. Notice there's something common here. If we take the operations we've learned in school, we have addition and subtraction as our base level operations. We learned those earliest in school. And then we did multiple addition, in other words, addition repeatedly, and we call that multiplication, and the inverse of that is division. Okay, so this is in a sense sort of a higher level operation. And then we had repeated multiplication, and those are exponents, and then the inverse of that is roots. Okay, so we have sort of a hierarchy of operations. Now we encountered this when we did order of operations. We said that these kinds of operations go first, then these, then these. That's just sort of an agreement on how to interpret expressions. But here what we're seeing is I can do a multiplication by actually carrying out an addition problem. So in other words, we can do multiplication by adding. We can do division by subtracting. Isn't that interesting? Okay. Here we've seen that we can do an exponent by multiplication. And one thing that's not listed here is we can do a root by a division. In other words, we can do all of these operations and it'll lower them one notch. So in reality, logarithms can be very useful for reducing the complexity of a problem. In fact, this is historically why logarithms were originally invented. Logarithms were used in order to do multiplication of big multi-digit numbers before the time of calculators. You just look up the logs up here. You'd look up the logs of the two numbers and add them, and that would be the log of the result you're looking for. So you just look up the result and look it up backwards in the tables, and you would get the result you want. Let's look at each one of these in a little bit more detail. Okay, notice that the log of the product equals the sum of the logs. Looks a lot like what happens with the exponents in a regular exponential kind of a problem here. So we're adding exponents in order to multiply two numbers. In fact, we can structure a proof of this statement based on this statement. So for instance, if I take this entire number, and let's call that A, and let's take this entire number, and let's call that B, then notice that for the base B, x is actually the log of A. Okay? In other words, this is the exponent that this base has to be raised to give us A, right? And similarly, y is the log to this base of b. And so this would be, the y here is the log of b. All right? And so what we have over here is the result of a times b. And so this is a times b. And notice that the log of a times b is this exponent here. That's just x plus y. But what is x plus y? It's the log of a plus the log of b. So more than just an indication of a proof, this actually is the proof. But there you have it. So in other words, the log of a product is the sum of the logs of the two factors. Okay, let's go on to division. Okay, let's look at the quotient. The log of a quotient equals the difference of the logs. So just like multiplying reduced to adding, division reduces to subtracting. And again, it looks like the laws of exponents here. And we're going to follow exactly the same pattern. We can just treat this as a, and we could treat this as b, and therefore x equals the log, with using this base, the log of a, and y is the log of b. Okay? And notice that this number is the quotient. This is the result of a over b. So this equals a over b. So if this is a divided by b, we get this result, which is a over b. And notice the log of a over b. So the log of a over b is this exponent, x minus y. But what is x minus y? X is log of a, y is log of b. So that's log of a minus log of b. Okay? Again, the logs and exponents have very similar rules. In fact, if you know that any log statement can be rewritten as an exponential statement, it makes sense that the laws of exponents should carry over to the laws of logarithms, and they do. Now this one we did already. I want to show something else about it, however, so I'm not going to do a proof of it here. But notice that one way of looking at the log of a to the x, let's do it for whole number values of the exponent. So say if it's a to the third power. So the log of a to the third power could be thought of as the log of a times a times a. And you can extend this to any number of factors there as well. Okay, but what do we know about this? The log of a product is the sum of the logs. So that's the log of a plus the log of a plus the log of a. But that's just 3 times the log of a. Okay, so that makes it very intuitive and reasonable that this should be the rule. That x times the log of a is simply saying we have this many log of a's added together, which is following the rule for repeated multiplication applied to logarithms. Okay, the limitation of this line of reasoning is it's limiting us to whole number values for x. The original proof we did in the previous section didn't have that limitation. So even when x is a half or minus 1 or things like that, it's still a true statement. So basically, the log of anything to a power, you can bring that power out to the front. And boy, does that simplify things. This is probably the most used property of logarithms in the modern day world. Logarithms were used to simplify calculations before calculators, but in terms of things that are still useful for analyzing expressions today, this is probably the one you'll use more than any other. I just want to extend this rule to show explicitly how we can get the log of a root, okay? So this is an addition to what's in the book. So the log of, say, the nth root of a, it's going to be the log of a divided by n. And how can we see that? Well, it's a very simple application of this rule. Notice that roots reduce to division just like power is reduced to multiplication. Okay, you can see that right away if you notice that the nth root of a could be written as a to the 1 over n power. So the log of a to the 1 over n is following this rule. You bring the exponent out to the front, 1 over n times the log of a, and then I can just rewrite that like this if I want. Okay, so in other words, powers and roots, division and multiplication, all of them can be simplified using logarithms.